Okay, we're going to start talking about AC and DC circuits today. Here we go. So we're going to describe the difference between AC versus DC. We're going to talk about electric hazards and the human body, and we're going to talk about nerve conduction and electrocardiograms. Okay, AC versus DC. So far, we've only considered situations with constant voltage, where you have a 9-volt battery and that's your only source, and as soon as you plug it in, you just have constant 9 volts. This creates a constant current, V equals IR. We call this direct current. It flows directly from the plus to the minus terminal on the battery. But there's another type of current and another type of voltage, which is time varying or alternating voltage, which sets up an alternating current. So there's a difference between if the positive terminal and the negative terminal, the electrons just flow directly over there in an AC circuit, and you'll see it with a little squiggle like that, plus and minus. There's your circuit. What the electrons are doing are there, these guys there, these guys there. So everything's jiggling back and forth rather than setting up a constant current. So this is how it would look on a graph. Your voltage and your current would be just constant. There's a current, there's your voltage. On DC, it's just over time. You're reading the same value over and over again. With AC, you can see that you go to a maximum voltage to 0, to a minimum voltage to 0, to a maximum voltage to 0. So you're just pushing, pulling, pushing, pulling, pushing, pulling, pushing, pulling. This looks like a sine wave, doesn't it? Wouldn't you agree? Sine of 0 is 0, so at t equals 0, you're getting 0 voltage. AC voltage is given by this equation. You can model that graph with sine of 2 pi ft. Remember that sine is whatever number you put inside sine. The output is between -1 and 1. Every result you get, it could be 0.7, it could be negative 0.6, whatever it is, it's between -1 and 1. So if you multiply that by V0, now it goes between plus V0 and minus V0 because it's multiplying the sine function, which goes from +1 to -1, is multiplying it by V0, so now it goes between plus V0 and minus V0. So this is the generic formula for that. The 2 pi is a constant, the t is your time variable, and then f is the frequency, or how quickly it's oscillating. You can get the same thing for current, I0 sine of 2 pi ft. So the peak current is given by the peak voltage divided by the resistance in the circuit. So if we go back to this graph here, there's your peak voltage, and if you want to know your peak current, it's just V equals IR, V0 equals I0R, so your peak current is just going to be V0 over R, and that will calculate that point there. But these graphs, this graph here is sine, okay, of 2 pi ft. If our frequency is higher, the wave will be closer together like that. If the frequency is lower, it's going to be more like that. And those numbers can change. You just change f and you can change the shape of your graph. Okay, so current in a resistor oscillates back and forth just like the voltage does, and V equals IR, you can calculate that. A light bulb is a resistor. A light bulb resists the flow of current, and when it does it, it takes energy, and that energy is converted into visible light. The electricity coming into your house is AC, and fluorescent lights, like the ones in the room you're in probably, flicker. They go plus V minus V, plus V minus V, so they cross 0. And this flickering is because they're actually switching on and off quite often, 120 times a second actually. Incandescent bulbs, like regular light bulbs, like the old ones, glass with the filament, even though the voltage goes on and off, the way they glow is by heating up the filament. So the heat doesn't turn off and on once it gets hot. So an incandescent bulb just glows a constant amount. But a fluorescent light will flicker, and an LED will flicker. Okay, so since light output is fluctuating, that also means that power output is fluctuating. So if the light bulb is dimming and brightening, then the power is dimming and brightening as well. And so if this is your power versus time in an AC circuit, you can see it's not a constant amount of power. You're emitting a maximum and a minimum and a maximum and a minimum and a maximum and a minimum, and then this is your this is your average power, actually, is that line. So P equals IV, current times voltage. Then if I just multiply those two sine waves together, I just get I0 V0 sine squared 2 pi ft, and that gives me this function. Okay, and notice it goes from 0 to a maximum value. It's not actually from minus, because you can't have negative power. You're always putting out power even if the voltage is going plus and minus. Okay, so instead of caring about power fluctuation, we generally care about the average power output. The average power is just half of the peak current times the peak voltage. That's easy. We can also define an average current and average voltage. We call these RMS values, which stands for root mean square. It's a fancy word for a fancy type of average. So you are normally used to taking the average of, let's say, three numbers, first number plus the second number plus the third number divided by 3. The root mean square is just the first number squared plus the second number squared plus the third number squared divided by 3 in this case, and then square root. If we had 4 numbers, it would be divided by 4. If we had 5, it would be 5. In any case, it's still like an average, but it's the square root of the numbers squared. So it's a little bit different square root, but we want that for, we want a positive value, so we square everything. So what's the point? IRMS is I0 divided by the square root of 2. So whatever your peak current is, just divide it by the square root of 2 to get your IRMS value. And then your VRMS value is just your peak voltage divided by the square root of 2. And then your average is just, if you multiply two of these together, you get that. And then if you do that, you see that the square roots of 2 times square root of 2 is a half. So you just get I0 V0 times a half, which is what I already showed you for the value of the average power. So in general, use RMS values instead of peak values. So for example, in general, we use this. So if you get 120 volts into your house, that's your VRMS. Okay, so if VRMS divided by the square root of 2 is equal to your actual voltage, then you're going to have 120 volts is equal to V times the square root of 2. So you want to figure out what your actual voltage is. So if your 10 amp circuit breaker says it's rated for 10 amps, that's actually not your peak current, but if your sustained current goes above 10 amps of RMS, a sustained RMS of 10 amps or higher. So that means, so if you have a graph here, I think we've got a graph of the, they don't have a graph with the RMS value on it. But if this is your graph, then your RMS value is usually about there. Okay, so if it's 10 amps, you could have a graph that's like this, but if it's a little bit higher like that, then you're going to trip your circuit breaker. So if you get your hair dryer and toaster going at the same time, and then you microwave something while you're doing laundry, you know, on the same circuit for some reason, then you'll trip your breaker. Okay, so in your house too, when you look at the power rating of your devices, like when you buy a TV, there's usually like the Energy Star rating on there of its energy usage. That's using the average power and the average voltage and the average current, so the RMS value. All right, voltage and current RMS values are the DC analogs of voltage and current. So when you calculate resistance and voltage and current, generally we want to use the RMS values for talking about current and voltage in an AC circuit. So that's your big difference, is AC versus DC. What do you use? Make sure you're using VRMS and IRMS when you're doing V equals IR type problems, unless otherwise stated, like asking what is the peak compared to the regular. Okay, we use AC generators at power plants because it is much easier to step up and step down voltages with AC than DC. So that's if you're wondering why do we use AC. For example, you transmit power at thousands of, tens of thousands, hundreds of thousands of volts and low current, and when it gets to your house, you convert it into 120 volts. So generally you'll step it down to thousands of volts to hundreds of volts to 120 volts at various transformers in your house. Outside of your house, sorry, substations and so on. Okay, but that's your main thing, is you're going to want to be just calculating VRMS and IRMS and using that equation V0 sine 2 pi ft. Okay, it's not scary, it's just a sine wave. Okay, so electrical hazards in the human body. There's two main hazards, thermal hazard and shock hazard. The thermal hazard is when you have too much power and it heats something up. You can start a fire, you can get burned. That's a thermal hazard, space heaters, right? So whenever electric power is converted to thermal energy and can't dissipate the heat fast enough, you have a thermal hazard. The classic example of this is the short circuit. If you connect a circuit with very little resistance, then all of your power is straight from the voltage V squared. So you've got 120 volts squared. That's your total power. Your resistance is very, very, very small. So you end up multiplying that even more. And that gives you the short circuit, and that's bad. A shock hazard, on the other hand, can stop a person's heart. It also burns. If the lightning goes through you, it'll burn your tissue from start to finish. So the major factors that you worry about when you're dealing with shock are the amount of current, the path taken. Did it go through your heart? Did it just come through your hand? The duration, how long were you being shocked for? And then the frequency of the current. And for a DC circuit, the frequency is 0. So this is, if you play with the electricity, shove a fork into your 120 volts, all these calculations are for that situation. So 1 milliamp will give you a sensation. 5 milliamps is less than that, will be fine. 10 to 20 milliamps will start to contract some muscles for you. At 50 milliamps, it'll hurt. At 100 to 300 milliamps, you could have issues with your heart, depending on the path it takes. 300 milliamps, you'll get a burn, depending on how much and how long. And then 6 amps will just mess you up. You have usually 50 amps, maybe 30 amps in your house coming into it, and 10 amps or so, or 20 amps on any given circuit. So you don't want to play around with the electricity in your house, but I will say too that V equals IR, and if you have a lot of resistance, that can help protect you from you might not have enough voltage at 120 volts to actually push the current into you. So this is assuming the resistance is low enough that that current can flow in you. And so this is a plot here showing you the effect of the frequency on your damage. And so you need to start getting more and more and more current when the frequency goes higher and higher and higher before it causes an issue. So let's talk about nerves really quick. So nerve conduction relates to how electrical signals are carried by the nerve cells. A neuron is a little bit different than other cells. It has tendrils that can connect to other neurons. The signals either jump across a synapse or across a dendrite. This simulates a cell once it gets there to do its own thing, and then it could be sent from an axon to another nerve cell or muscle cell. This is a general schematic, and you're going to do a lab, I think, where you try to model this, where each of these here you can treat as resistors. So if you have like 10 volts from here to here, then you might have 3, 6, 9, or 3.33 volts, 3.33 volts, 3.33 equal resistors in series, and you'll have these voltage drops across each of these nodes of RAN VA. So this is just your diagram of it. So the signals in your body, they're more complicated than just an electron moving around, but you can understand it with two mechanisms that we already know about: Coulomb force, which is the force between charges, and then diffusion, which is the concentration of salt ions from one spot to another. It'll want to flow from the high concentration to the low concentration. So you can create a potential difference across a cell membrane, and then the free ions will want to move from the high concentration to low concentrations. But the membrane is semi-permeable, so not all of the ions will pass. and you can end up with this plus and negative potential across it, and that creates a voltage. And then as these ions get pushed in or pushed out of the cell, it can generate a pulse. So the separation here, you could have a potential difference of only 70 to 90 millivolts or so, but you're 8 nanometers thick at that level. And so if you calculate the electric field where the voltage is 70 or 90 millivolts, but the distance is only 8 nanometers, that's a very strong electric field on the edge of a cell. And as these ions move in and out of the membrane, it generates a current, and it'll depolarize it when sodium, for example, neutralizes, making it positive, and then potassium will come back in, repolarize it. Let me go to this section of the book so we're on the right page. Okay, and then this sequence of events results in a voltage pulse, which is called the action potential. And we've got a picture of it here, which shows the voltage as a function of time. So there it goes, and then whoop, there's that pulse, and that happens when the sodium rushes in and the potassium comes in too after it. Okay, so that's just information that you should know. This is just another diagram showing those same things, and it just talks about echocardiograms after this and how they work. So just to measure you're getting a voltage from your signal, and we can convert that into understanding how your heart is beating. So this just talks about the ECG a little bit, and you can read that if you'd like. Otherwise, that's the chapter. So main things: VRMS, IRMS. Be able to get the peak voltage from IRMS or VRMS, or vice versa. Be able to get the RMS from the peak voltage from those equations, okay? But they're pretty straightforward equations. We get them all here. So, yeah. And then get the power from that. That's it. Current, voltage, power in an AC circuit. Okay, I'll see you guys later.